General description. So at the core of the discipline of modeling and simulation is the fundamental notion that the models are approximation of the real world. One thing is a very famous quote from someone that all models are wrong, some are useful. So models are just mere approximation of the real world. What we can do is that right now, as I did for COVID, is data-driven models. So the more the evidence, the better the modeling. So I did 5 modeling attempts for Sindh, and I did 4 modeling attempts for Pakistan for COVID cases, for number of deaths, for number of recoveries, for number of hospitalizations, for number of critical care patients. But I did it again and again, and so my initial models were over projecting, and my middle models were under projecting, and right now I'm kind of doing a better job. So models are approximation of the real world. Why we do model? We can't let people die and then see the effect of disease, or we can't just wait for the last moment when, say, there are 50 admissions in one hospital and they don't have any bed over there, or they don't have any person who can run a ventilator machine or operate a ventilator machine, or they don't have any one trained staff right at that point in time. Say surge for corona is expected in the middle of July. So they would have to train their paramedical staff. They have to train their doctors and their, especially the supporting staff, to how to handle the load of patients and how to handle the attendants in the gravity of that situation. So we, rather than just going till the very end, it's always good to do a modeling, and it's always good to do a guess of the situation and then act promptly according to that guess and be prepared for what would happen next. Okay, in turn, the model can be modified when the simulation allows for repeated observation of the model. Okay, what is the basic difference between the modeling and simulation? So what I understood so far, I've been doing modeling for 16 years, and what I understood so far is modeling is setting up the structure of the problem. Simulation is solving the problem again and again. So repeated solution of the problem is called simulation. And then we see at every repetition, so how the system behaves. So this is just modeling is a structure. Simulation is solving that problem, solving that structure, and giving us giving us solution, and we will decide which one of them are feasible, one of them are not feasible. A very quick example would be solving a quadratic equation of time: t square minus 3 minus t square minus t minus 6 equal to 0. So one of the roots would be negative. So it's 2 times 3 is 6, or 6 times 1 is 6. So one of the root might come negative. And what do you mean by negative time? So time is a physical quantity which can't be negative. So in that case, we need to decide which one of the simulation or which one of the solution in that particular example is feasible and which one is not. After one of many simulation of the model, analysis take place to draw conclusion, verify and validate the research, and make recommendation based on various simulation of the model. As a way of representing data, visualization serves to interface with the model. Nowadays, there is a lot being done for visualization. There is a lot being done for representation. So dashboards are there for visualization. There are VR-based simulations for visualization. So visualization. So as it is said that a picture is worth 1,000 words. So it's important to visualize things, and nowadays we have enough computing power and simulation power to visualize bits. Thus, modeling simulation is a problem-based discipline that allows for repeated testing of a hypothesis. We can test it again and again, so we can simulate it again and again to see what happens. The foundation of an modeling and simulation course is built upon 4 precepts: modeling, simulation, visualization, and analysis. So we do modeling. Great, we have a structure, we have an equation, a setup. We did simulation. Okay, that's good. We did repeated observations and then see what happens. We visualize the results. Okay, this is the end result. But what is 4? What does 4 means? 4 means the color would be lightened. 4 means the structure of the building would collapse. The 4 means these rods might twist. 4 means this chemical, if the concentration or the ratio becomes 4, you might not get good results in your fabric. 4 can mean anything. So visualization is important, and the last but not least is the analysis. So how credible your results are. What are the main terminologies? A system. What is a system? System is a part of some potential reality where we are concerned with the space-time effects. So that's why I was asking about spatial. So spatial modeling deals with the space, and temporal modeling deals with time, and spatio-temporal modeling deals with the space-time effects. And causal relationship among parts of the system. So our system is usually defined by a boundary. Say, for example, a bank could be considered as a system that has a boundary, which is the building of the bank. So outside that building, bank doesn't exist. So the hierarchy and the protocol of everything exists within that building. So that building of the bank, we can consider it as a system, and system usually has a boundary which separated from the universe, and that boundary makes system a closed world. So there might be some immigration, there might be some emigration, there might be people coming in, there might be people going out, but the hierarchy and the protocol of that system would actually be based on that building in this example. Say, for example, um, more formally, a system is defined as a group of objects that are joined together in some regular interaction towards the accomplishment of some purpose. Say, an automobile factory, we would have machines, we would have company parts, people working jointly along the assembly line. So assembling the distinct parts of the car or the automobile to first, build the frame, and then assemble the engine, and then assemble the transmission, and then assemble different electrical and mechanical based systems. So all of these entities and all of these group of people are working together, and all of these machines are working together to deliver one task, which is actually um, you know um, manufacturing a car in this example. A physiological system would be a better example to give. You have cardiovascular system, you have respiratory system, you have musculoskeletal system, you have nervous system, you have renal system, renal clearance system. So all of these systems are acting jointly to make you work, to make you do daily chores, to help you keep yourself alive. A system is often affected by changes occurring outside the system environment. Say, for example, an example of a factory, the system behavior might change because of the orders, because of the credit crunch, because of the nature of work. So the system's behavior might change due to external agents that actually occur outside the system. So effect of supply and demand. Alhamdulillah, we are selling plasma nowadays. Alhamdulillah, we are selling a pulse oximeter, which is usually between 800 and 2000 rupees. We are selling it up to 10,000 rupees. Oxygen cylinder, 3 to 5,000, available quite easily. You need to order it after 1 or 2 weeks before, and the price is usually 20 to 28,000 in Karachi, and in Lahore, I came to know by someone that is 42,000. So this is how things affect on a system. External human body invasion of pathogen. When you got infected, your normal regulatory systems get affected by something external. Your body started to build a secondary immune launch if pathogen is quite virulent. Otherwise, it could be eaten by macrophages and at the first line of defense of our body. So this could be thought as another external agent that could affect a system. Now, entity. What is entity? An object of interest in the system is called entity. Say, customers entering at a bank, customers present at any point in time at a bank, they could be thought as an entity. Okay, so what is an attribute? The property of an entity is called an attribute. So a customer would go to the bank and check account balance, ask for checkbook or any other thing. So this is an attribute of an entity. If you have a chai ka hotel, and so the service of that chai ka hotel would be thought, the people serving the customers would be thought as entities. An attribute is how good they are in you know uh, placing your order or something like that. An activity is represent a time period of a specific length, managing bank deposit. So activity is just the collection of operations that transform the state of an entity. So the state of entity could be changed by an activity. So it's a mere definition. A process, what is process? A process is a sequence of events which are ordered in time. So you go to a mart for shopping, you pick up a couple of grocery items, you get into the line for a payment, you pay the price, you get the receipt, and you get your grocery or items, whatever, and then you get out of, you leave the mart. So these are a couple of events which are sequenced in time. So process is a sequence of events which are ordered in time. What is an event? Because we just read event over here. So changes in the system, arrival, beginning of a new execution, departure, these all are events. There are two types of events: endogenous events occurring within the system, exogenous events occurring outside the system. Now, these are definitions. The most important definition is the state variables. The state variables define the state of the system. We can start simulation from a state variable. Uh, the length of a job queue could be thought as a state variable. State variables are very important. I will stop here for 1 minute and show you an example for a state variable. Say, uh, would resort myself to. Okay, so this is. I hope it is visible to all. Hmm. So this is a state variable. It has four state variables. This is the corona model I did for Ahan. Susceptible, exposed, infected, and recovered. So if we consider corona as a pathogen and um, infecting a person till it recovers or till it die as a system, as a process, a sequential set of events, then a person was susceptible, so it was prone to infection. Then it contact with some infected people, and then it get exposed. So there is a defined incubation period for COVID, which is 10 to 12 days on average, but it can be up to 19 days and it can be up to 4 days. So it's a quite variable thing, the exposed period. So so you were susceptible, then you get contact with some infected person and you will get exposed. So you were at susceptible state at the beginning. After some time you are in an exposed state, then you remain exposed state for 8-10 days, and then symptoms start to build up, and then you will go into infected state. So this is the third state. So susceptible is a state variable, exposed is a state variable, infected is a state variable, and recovered is a state variable. So you go from exposed state till infected state, and you stay there for about 8 to 10 days, and then you start getting recovery, and then you move from infected state to recovered state. So SEIR, these are state variables, and your speed from, or your rate from transforming or traveling from S to E is dependent upon a parameter called beta. Your rate uh, of transfer from E to I is depending upon some rate gamma, and your rate from of transferring from I to R is depending upon some parameter which is delta over here. So S, E, I, R are state variables, and beta, gamma, and delta, these are parameters. So for a dynamical system, state variable has a specific meaning and parameter has a specific meaning. So this picture would show you all of it. So the state variables are four over here. These parameters beta, gamma, and delta could be thought as say for example you have underground tank, water tank, and you have an overhead water tank. So you have two water tanks. So the quantity, so that underground water tank could be thought as one state variable, and why it is a variable, because the amount of water in the underground tank would fluctuate over time. Similarly, at the overhead tank, the amount of water would fluctuate over time, so that's why they are state variables. So they are giving me state of water present in underground tank and a state of water present at any point in time at overhead water tank. So that's why they are called state variables. And you got water from, and you are very fortunate, and you got water from the government at a certain date or at a certain time. So that actually that incoming would be thought as a rate, some rate of water coming in, say for example, an hour could be drawn to S. So if it is your underground tank, the water is coming in from outside, and then you set up the motor, and then the water is actually get transferred to the overhead tank. So the diameter of the pipe and the horsepower of the motor could calibrate beta. So the more the horsepower of the motor you get for the overhead tank, you will get more water displaced per unit time in the overhead tank from the underground tank. So this could be thought as a state variable and as parameters. Coming back to our slides, state variables define the state of the system. Can we start the simulation from state variable, say length of job Q, say for example. What is the discrete system? The discrete system is one in which the state of variable changes only at discrete points in time. So I show you SEIR system. So the number of patients or the number of people in susceptible compartment, they cannot be 55.7. They would either be 55 or they would either be 56. So these are discrete set of points. What is the continuous system? Cardiac activity, head of water behind them, urinary firing, respiratory movement, daily temperature variations. These all are example of a continuous system. Oh God, there's a typo. It should be continuous. What is a model? A model is a construct of conceptual framework that describes the system. The model takes a set of expressed assumptions. Model is usually mathematical and logical. Model is usually symbolic. The last point is very, very important. This is all of the crux of modeling. A model can be used to investigate a wide variety of, oh God, VARIETY. I hate typos and I have typos in my own presentation. I'm sorry for that. A model can be used to investigate a wide variety of what if questions about real world system. So what are what if questions? Potential changes to the system can be simulated and predicted. Their impact on the system. Find adequate parameters before implementation. So we can do beforehand safety measures before any God forbid bad thing happens. There can be two types of model. Physical model. Physical model is something that exists. Say for example, I need to if you look at Dr. Jaffrey, he has a working model, a prototype model of an engine in his room. So the model can be physical, a prototype of some real system, or a model can be notional. So a notional model could be a logical statement or a mathematical equation, or a notional model in a much broader sense. So you don't have a bank branch, or you don't have a outlet of a certain chain, a very big fast food chain at a place, and we could always model what would happen if we open a fast food chain in at that street, at the near that market. What would be our sales in the next 6 months, and when will we reach to the break even? So all of these type of questions could be thought of as a notional model, because that branch doesn't exist at that point in time when you are making models. So, but when you are using physical models, then those planes exist, and you need to do a certain type of change in uh, the design or something, and you need to see that. So it's a notional model are more, uh, if you don't understand it properly still, physical model are those which exist um, while we model, and mostly notional models are something that actually we perceive in our heads. Simulation has a lot of definition. um, a method imitation of implementation of a model over time. This is actually what I spoke earlier. A technique for testing, analysis, and training, where real world and conceptual systems are reproduced by a model. An unobtrusive scientific method, inquiry involving experiments with a model rather than with the portion of reality that the model represents. गाड़ी की छत के ऊपर अगर, so if you have a car, and if you drop a really heavy object in the middle of the roof of the car, then how would it deform? What would be the pattern of the deformation? Would it actually harm the passengers that are sitting inside? So rather than throwing things at the roof of the car, the best thing is to do modeling on or and simulation on a computer rather than doing actual tests. Live experiments are very important, but we can the cost of live experiment would be dramatically reduced if you do simulations in addition to live experimentation. A methodology for extracting information from its model by observing the behavior of the model as it is executed. This is a very important aspect. We see what is actually happening in a simulation by executing it. So there are some types of model. The best guess is gut feeling. मेरी अम्मी ने कहा था. I was always thinking about that. This is the first type of model. Statistical models, time series model, statistic. So statistic model, the mechanics, if you have read by R.C. Hibler, there is a distinction of dynamic models and static models. We would be dealing with dynamic models in almost all of the course. We didn't look much. We won't look much into static models, but static models are if a rock is at the corner of a mountain, and the sum of forces and the sum of torques acting at a certain point on the rock are zero, then what is the chances of the rock falling down from the cliff or from that end? So these type of problems where we use fundamental principles of equilibrium, or if there is a cantilever beam or there is a truss, um, and a certain load is applied to one end of a cantilever beam, then what is the chance of the cantilever beam from bending, and at what point along its length, along its axial load, uh, which it bends. So these type of questions are dealt with static model. Time series model, they deal, as the name suggests, they deal with time, what would happen next, what is the periodicity of the system. If you draw the temperature curves per day, so that would be per hour, per minute, or if you consider annual cycle, so per day, then you will get a time series model of temperature. Neural network, this is a very interesting model. It is basically network based models, which is actually happening right now in our brains. Disease models, COVID-19 model, we will talk about this in much detail during the course. I have developed a plethora of models. Even if I didn't do anything in the course, I can only speak about COVID for 10 sessions. Expert systems, combining all other observations. Expert system, they take decisions by themselves. These type of systems are called expert systems. Artificial neural networks, ANN based systems, game theory, fuzzy logic. These type of rules help us develop expert systems. Um, Simulation models, these are the models which we will be discussing in the course. This is a typical structure of a mathematical model. We have a physical problem, we have a differential equation, and then we have a solution of the problem. In the meanwhile, during that process, during that journey, we identify important variables. We make reasonable assumption. Say, for example, let me give you an example of identifying important variables. When the when COVID-19 hits at the beginning, I thought it would wear off after some time because of the temperature. But it turns out that temperature has almost negligible effect um, in corona persistence and corona establishment in the community, in the local population. So I thought that was an important variable, and I modeled that as well, the effect of temperature. But after some time, I realized that there is no effect of that. So identification of important variable is a must. Make reasonable assumptions and approximation. I thought there will be 20% decline in cases if the community is sensitized. If the number of deaths crosses 1,000, I was expecting that the transmission rate would decline to almost 20%, because if the number of deaths hits the number 1,000, the people will be more careful about that. So that was my assumption, and that was my approximation. One of my approximation was, okay, on average length of stay in a hospital, if God forbid, if someone is hospitalized, so what would be the average length of stay? So I thought about that. Initially I thought it as 6 days, and then I thought, no, there are some of the people which are staying longer, very much longer, they're up to 20 days. So what I did, but there are some people who only required oxygen for about 4 to 5 days. So what I did is that I set it up to 8 days then, and I set the standard deviation of 3.5. So if you consider it as a normal distribution, then 66% of the patient uh, would be requiring 8 days plus 3.5, so 8, 9, 10, 11. So 66% of the people which are being hospitalized in sin. So, and if we subtract 3.5 from 8, I think it's 7, 6, 5. So between 4.5 and 11.5 days, I would expect 66% of the patients. If you remember, mean plus minus standard deviation, mean plus minus one standard deviation uh, takes into account for about 66% of the population. Mean plus minus two standard deviation would take into account about 95% of the population, and mean plus minus three standard deviation would take into account about 99.95% of the population, if the distribution is unimodal and symmetric. If the distribution is unimodal and symmetric. So I was assuming that there are a lot of people coming into the hospital, and rather than exponential distribution, if it is normal distribution, then their stay would be around 8 days. So I set mean to be 8 days, and I set my standard deviation deliberately to a large number. 3.5 is a big number, so I set it deliberately to a larger number to account for the people which are overstaying more than 8 days. So this is actually uh, thinking about the problem to make reasonable assumptions and approximation. Apply relevant physical laws. Yes, this is important. If a person is susceptible, then it will get exposed, and then it will get infected, and then it will get recovered. This would never happen that a person is susceptible, it will get recovered, and then it will get exposed, and then it will get infected. This won't happen. So the relevant physical laws should be there, and we should obey them. The person in recovered compartment can't be negative. Time cannot run at the other direction. It's a unimodal, unidirectional thing. So we need to look about the physical laws as well. And then after doing all of this stuff, I wrote differential equation, solve differential equations, apply the boundary conditions, get the solution, and then retransform the solution into the physical problem. If you model a system, a model of a system is used to study the system. In experimental studies, sometimes it is possible to experiment with the system, although it is not always possible. Bank, factory, human. A model is defined as a construct of a conceptual framework which describe the system. Now, I would like to actually everyone of you to pay attention in the graph. So, modeling depends upon the research question. So, for what I did in modeling for COVID, I didn't take into account for the reinfections. That was the question asked someone from Columbia University to me. So, I didn't take into account reinfections. Why? Because I'm not interested in reinfection right now. I didn't take into account the second peak because I'm not interested in second peak right now. I didn't take into account the demographic turnover, the births and deaths over time, because I'm doing it for 1 year only. So you need to decide what type of uh, questions you have and what type of model you need to develop. So you look at the it's, I think, Massachusetts transport. Yes, it's written over here. So if you look at the underground or subway, the route of transportation, I think it's for subway or some for some buses. So route of the transmission to transport. So on the left hand side, this is the actual situation. On the right hand side, this is the model. So model is a simplified version of the left hand side. It represent it misrepresent distances and directions. You can see that it has it is slightly different than the original situation, but the distances and directions are not the question. The question is actually showing the connectivity. So that displays the connectivity really well. So our what we want actually at that point, we what we wanted is connectivity. So how two stations are connected, that was the question. So that's why we developed this model. If we had to develop something that is related to the distances and direction, we would develop a separate model which takes into account the original location on the map for the separate stations. This is a flow chart. You can look at it. Okay, so these are a couple of important slides, and then we would just move quickly. So there are some decisions. What type of model we need? Do we need a deterministic model or we need a stochastic model? So what is the difference between the deterministic and a stochastic model? Uh, Let me give you a very quick example. Um, so this is an example of a deterministic versus a stochastic model. So you can see the plane lines. These are deterministic. So the red line, the green line, and the uh, black line, they represents the deterministic solution of the system of a SEIR model. This is an epidemic model, and the dotted line shows the stochastic part. So stochastic version of the model means that a stochastic, if we repeat the experiment, so the concept of simulation is actually stochastic. So if we repeat the deterministic version of the model 1 million times, we will always get the same line. It's over here. The green one, the red one, and the black one. But if we repeat the stochastic version of the model, so for every repetition, although the initial conditions are same, they all are started at the same point. You can see that, but the trajectory would change slightly for every run. So if I run it for 100 times, I will get slightly different 100 different solutions. If I run it for 1000 times, I will get slightly different but 1000 solutions. So you can see that the deterministic peak is definite around at 12 days. But the stochastic peak may range from 8 days till 12 days or 13 days. So it's good to talk in intervals rather than an absolute number. So this is an advantage of using stochastic model. So the decision is important, that whether we have to use deterministic or stochastic, and whether randomness. You can see that the trajectories are different, so they are different because of the randomness. So whether randomness is important or not. One more thing is this: is the system static or dynamic? So this is very important. But we would be talking in all of the course. We will be talking about dynamical system, in which time is a significant variable. Continuous and discrete, I'm not talking about that. You know it very well. Do you mean by continuous variables and what do you mean by discrete variables? So if you look at this structure, we would be looking at Monte Carlo simulations, which are part of static modeling, and we are looking at discrete event simulation, which are a part of stochastic. So we look at two different stochastic bits, in the course. And all of the stability analysis and all of the continuous models, if, let me go back. So all of the stability analysis, all of the continuous modeling is basically deterministic. And the Monte Carlo simulation, discrete event simulation is all stochastic. So we will deal with both type of systems. How to develop a model? Okay, just have a read at it by yourselves. Modeling levels, conceptually very high level, specification, paper-based models, computational, computer programs. We usually need to use some language for that. What is verification and validation? Verification is a very important bit that actually questions about modeling structure. So did we build the model right? And validation is actually deals questions about the application of our model, or more towards the simulation of our model. Whether, say for example, there was a model developed by Imperial College that shows that 80,000 people would die in August. I really want to shoot that person on face, because that model created a lot of mental health issues in Pakistan. And since the name of Imperial College is associated with that, people are really, really, in a very bad mental condition. So we need to validate it, whether it is saying what it is. So that model by IHME, it's an organization. So IHME modeled that on 22nd of June, there would be 3,000 deaths on a single day. Just on 22nd of June, in Pakistan, there would be 3,000 deaths. We only had 3,500 deaths so far. The cumulative number is 3,500. And then they said that no, on the 22nd of June alone, there would be more than 3,000 deaths. So we need to validate whether the computational model, it should be consistent with the system being analyzed. It should be consistent with the observations. In other words, the empirical evidence, the model should support the empirical evidence, or the model should support the data. Now, this is the hierarchy of what we actually read. This is model, this is simple simulation, these are results, and these are insights. So it's a feedback loop that goes on and on. This is VV&A, verification, validation, and analysis. VV&A. Just ignore that. So what are the advantages of modeling and simulation? I'm not going to read this because of Abdurrahman, bore ho gaya, wo thak gaya. So the advantages of modeling and simulation, there are a couple of advantages, and I also talked about disadvantages. So there are a couple of advantages of modeling and simulation, and there are a couple of disadvantages. So say for one of the disadvantages, they can't ever completely recall real life situation. It's almost impossible. Not every possible situation may have been included in the model. So there was a disaster of, my memory is a bit impaired as well. So there is a disaster of Colombia, I think. Colombia, there was a space shuttle which was destroyed minutes after the launch. So the model suggests that temperature can't go to. So there was one solution from the model that shows the temperature and intermittent stability as a negative number, and they ignored that. And I think that another problem is they use different conversion system. So the problem was with the conversion system. So if you all know that there is a meter kilometer second MKS system, and there is an FPS system, foot pound in second. So there was some error in the conversion system, and they didn't take into account some of the solutions from the model, and because the probability of occurrence was very, very low. But actually that happened, and the shuttle destroyed just minutes after the launch. So not every possible situation may have been included in the model. Sometimes the equipment and software are expensive to purchase. So for this course, this is fine. But say for example, if you need to design a Formula race car model. Just like Dr. Riaz developed a ventilator, so equipment is costly. Experienced staff need to be trained how to use software and equipment. This is a dilemma, and I repeat, this is a dilemma of our society that I personally think this is a question of a debate. Um, I said it on many forums. Um, I think I think we don't have much trained people using ventilators. We need trained staff for ventilators. So this is my personal opinion, and I'm saying it bluntly that the people that are dying on ventilators are not mainly because of COVID. I think it's mainly because we don't have much staff. So this is my statement, and it's a controversial statement. But anyways, we need experienced staff and trained staff to use the software and equipment. And if you see that the advantages is one slide and disadvantages is two slides. Sometimes simulation results are difficult to simulate to interpret. Many simulation software have input analysis but no physical interpretation of the output. Sometimes we just have graphs, but we can't compare it to the real world situation. What are the benefits? Just read them by yourselves. When simulations are appropriate, um, this is important, and there are two slides of it, and there is one slide, two slides of when simulations are inappropriate. So it's all just theory, and I want you to have a good read at it. Read it as a book, read it as a novel. I know that it's not a novel, but try to read it just to make a sense of it, and that's all. Just go through it. Challenges of modeling. Modeling is not black magic. Modeling is performed to develop an abstraction of the system. There is a very old famous saying, garbage in, garbage out. So if you have garbage parameter estimation, you will get garbage modeling results. So the bad model is not bad. The bad model is bad because of you. And what is relevant depends upon our modeling goal. Say for example, we need to, sometimes there is a problem in the equipment, sometimes there is uh, some issue related to the modeling structure. So there are a couple of people who did COVID modeling and they didn't include exposed class. But COVID has a defined incubation period. So their modeling results were wrong because they didn't introduce that significant time delay. Okay, there are three characteristics and descriptors, and these are the last slides. Um, Fidelity, resolution, and scale. There are three properties. What is fidelity? Is how the model or the simulation closely matches reality. The more the fidelity of the model, the difficult the model would be to handle. So if you include a lot of detail, then the solution would be difficult. Handling the model or interpreting the model would be difficult. Attaining high fidelity is not easy because model can never capture every aspect of the system. A low fidelity is tolerated with regard to the components of the system that are not important to the investigation. So we usually compromise on the fidelity of the model. You can't model everything. It's impossible. You can't look into each and every detail of the system. It's quite hard. Second is the resolution. What's the resolution? The degree of detail the real world is simulated. Um, Say for example, the more the detail in the simulation, the higher the resolution, and it would be heavier for the computation in terms of computational sense. The computational complexity would increase. The model of an orange tree can begin with the representation of the entire forest, then the model of an individual tree, then the model of individual trees, fruit, leaves, each pieces of fruit in varying stage of maturity. We can do that, but that would require a lot of computational power, a lot of RAM. The third thing is scale. So, in a clothing factory, the simulation of a single sewing machine on the factory floor would consist of few simulation components, and it would require the representation of only few square feet of the entire factory. But if we need to look at the all of the factory, then that would require entire representation of machines, hundreds of simulation components spread out over several 100,000 square feet of factory space, and so on and so forth. So these are some attributes If the resolution is low, it could be thought as an example of a board game and a swarm. So swarm-based models, there are certain type of models called ant ant colony optimization, and there are certain type of models called particle swarm optimization. So they looked at bees, they look at ants, and they looked at the bird when they make a flock and then they fly together and do a cumulative task together, single task cumulatively. So these type of models are called swarm models, and these are agent based model because every agent act as a part of the system and system behaves as a whole. So these are some examples. I won't go in much detail. Just have a look at it. Important bit, the last thing, verification, validation, and analysis. So verification is the process of determining if the model accurately represents the conceptual description. Uh, the process of determining the degree to which a model is accurate representation is called validation. The process of accreditation, so either getting certificate from someone, either getting some sort of admiration, either comparing it, calculating MSE, mean square error, is basically analysis. So accreditation is official certification kind of thing. So these are some techniques. So the most informal technique is audit, test checking, walkthrough interviews or walkthrough test, reviews, inspection. More of inspections. More of them are slightly sophisticated are static. We use control analysis chart. There is a separate field in stats called process control, process design. We use data analysis. We use um, structural analysis. There are more of much richer methods which include dynamics. They include, say, statistical techniques, visualization and animation, submodule testing, module testing. So these type of are modern, and the more formal, we would never use that. So they are purely logic and mathematics. So we don't use these techniques in the real world. Okay, physics-based models in which physical laws are being considered. Finite element modeling, it's a separate course in which look at the structure is mostly used in civil engineering. Data-based models in which they are basically data-driven. We compare the data to the model output and then we train the model again and then we compare the data, and then as time passes, we again compare the data. The more the empirical evidence, the better the modeling. Agent-based models, ABMs, all of the games. Hybrid model, actually they took into account some of these modeling and combine them. So these type of models are called hybrid modeling. So they are classified into live, virtual, and constructive. I think this is not much important. We would talk about randomness in much detail in lecture number 3 and 4, I think. Yes. So that's all for today.